In this video, I want to show you more details on Euler's method, explicitly and more formally write down the equations that we can use to apply Euler's method, and show an example. So in the last video, I introduced Euler's method from an intuitive point of view, where we said that we're going to solve a differential equation of the form dy dx is equal to f of xy, given some initial condition y of x naught is equal to y naught. And we said last time that f of xy is the slope of our function, of our solution. So we're going to use this equation to solve for our solution. And the idea was we would take our old point, use the slope at that point to find some new point on our solution. So formally, that means that our update equation, which is used to go from one point to the other, takes this form. We update both the x and the y components. So x will go to xi plus 1, so some new x location is equal to the old x location plus h, where h is our step size. So that is our new x location is based on the old x location, and this is our step size, which is what's the distance between different points are on our solution, and that's something that we have to choose. Now we also have our update for y, so our new y location, so yi plus 1 is equal to the old y location, so the old point in our solution, plus the slope f of xi yi times our step size h. And in this equation we have y evaluated at xi plus 1, yi is y evaluated at xi, fxi yi is the slope at xi yi, and h again is our step size, the same step size used previously. And those two equations together allow us to go from an old point, xi yi, and compute a new point, xi plus 1, yi plus 1. And to do that, we use the slope. So the slope comes in there, and that's the f that shows up. And that is what we were doing graphically last time. But those two equations are the same type of approach. So let's use those ideas for an example. And the example that we're going to look at today is another fairly simple equation. So we have dy dx is equal to sine of x. And we have an initial condition y at x is equal to 0 is equal to minus 1. So that's our equation that we want to solve. And in this problem, I'm going to do the analytic solution. And we're going to do this so we have something to compare it to. So if we want to find the analytic solution of this equation, we can move the dx to the right-hand side of the equation. And we have the integral of dy is equal to the sine of x dx integral. So we just move the dx to the right-hand side and do an integral on both sides. And that gives us y is equal to the minus cosine of x plus a constant c. And how do we find c? Well, this is our general solution. We want to find our particular solution, and we're going to use our initial condition to find that. So we use initial condition to find c. And how does that work? Well, we say that y at 0 is equal to minus 1, which is equal to minus cosine of 0 plus c, which cosine of 0 is just 1. So minus, this whole term goes to minus 1. And so we have minus 1 is equal to minus 1 plus c, and therefore c is equal to 0. And our analytic solution is y is equal to minus cosine of x. There we go. That's our analytic solution of this equation. Now, if we have an analytic solution, we don't really need to do a numerical solution, but we can do a numerical solution, and this will give us something to compare to. So we're going to do this exact same problem using Euler's method now, and then we'll compare the results by plotting the two solutions against each other. So now we'll do the numerical solution. So now we'll do the solution using Euler's method. And to do Euler's method, remember, we wrote down our updated equations before, and we're going to use those. And the one thing in those updated equations that we need to specify is our step size, h, which in this case I'm going to tell you to use a step size, and we're going to use a step size of 0.5. And now we're going to solve the problem using a table. I'm going to construct a table. In this table, we're going to use it to compute our solution. And in the first column of the table, we're going to put I, where I is our iteration number. In the middle, we're going to have our x's. And remember that x plus 1 is equal to xi plus h. That's our Euler update for x. And then we're going to have y, I plus 1 is equal to yi plus f of xi, yi, all times h. And for this problem, f of xi, yi is given by sine of x, because that is the right-hand side of our original differential equation. If I go back up, you'll see that our original differential equation, sine of x, is our f. That's where f of x comes from. F of xy comes from. So that's where that comes from. And that, now we have our table and we're ready to go. Now, to get started, we need to start with our initial condition. So we're going to start with I is equal to 0. Excuse me, let's start with I is equal to 1. You can start with either, but it's easier in Matlab if you start with 1. So we're going to use a 1 for our initial I. X plus 1, we're going to have x1 is equal to 0. This is our initial condition. And we have y1 is equal to minus 1. And this whole line in our table is given by the initial condition. Now let's compute the next line in the table. So the next line in the table, we're going to have I is equal to 2. We're going to be looking for what is x2. And based on the equation at the top of this column, that's x1 plus h, which is equal to 0 plus our step size, which is 0.5. So x2 is just 0.5. If we go over to the y column, we can say that y2 is equal to y1 plus sine of x times h, which is equal to minus 1 plus the sine of, and I should have wrote x1 up here, it's the previous x location, which would be 0, and that's all times our step size. Now sine of 0 is just 0, so this just goes to minus 1. And now we have the next point in our solution using Euler's method. So I'm going to draw another line and we'll do the next point in our solution. So now if we set I is equal to 3, we're going to solve for x3, and that's going to be based on x2 plus h, which is equal to 0.5 plus 0.5, which is just equal to 1. And over here, we have y3 is equal to y2 plus the sine of x2 times h, which this is equal to our previous value for y2 is equal to minus 1, plus the sine of our previous x value, which is 0.5. And this is all multiplied by h, which is 0.5. And if we do out the math, this comes out to be minus 0.76, which gives us our next y value. So now we have 3 points in our solution, our initial condition, our point at x2, and our point at x3. Let's do one more line in our table, and then we'll show an example with our plot. So the last line in our table is I is equal to 4. We're going to solve for x4 is equal to x3 plus h, which is equal to 1 plus 0.5, which is just equal to 1.5. And we're going to solve for y4 is equal to y3 plus the sine of x3 times h, which is equal to minus 0.76 plus the sine of x3, which is 1, all times 0.5. And that, if you do out the math, comes out to minus 0.34. And this, we did the first 4 points in the table, but you can keep doing this process over and over and over again. By hand, it's very tedious, but on a computer, computers can do these number crunches for us very easily. So I wrote a Matlab code that solves this problem for us, and I'm going to run that Matlab code, and we're going to compare our Euler solution to the analytic solution. So on this plot, Euler solution showed with the circles, the analytic solution showed with the line, and you can see that they match okay. They kind of follow the same pattern. The step size that we chose, so originally we had to choose the step size of 0.5. If I make my step size smaller, let's make it 0.1, you see that the solution starts to match better and better. If I make my step size really small, these two solutions collapse on top of each other. So that kind of gives you a hint that the relationship between step size and the solution, the larger the step size, the larger the error. The smaller the step size, the smaller the error, but it requires more computations. So this solution took 300 steps to compute, which for a computer is almost nothing. So that was very fast, and it reproduces this result. And if we let it go further, so I'll just make my domain longer, you can see that these two curves are on top of each other for a very long time. If I made my step size bigger, we're going to have a lot of error, and the two solutions are going to start to diverge, although even that looks pretty good. Make it even bigger, they should really start diverging. So there you can start to see some divergence, but the key is if you have a small enough step size, the two solutions will match, and our numerical solution, computer using Euler's method, and the analytic solution will match, and we can solve very complicated differential equations using a numerical method like this. And that's the power of the numerical methods. They allow us to solve equations that we cannot solve analytically.